Hiya! So in this video, we're going to talk about the normal approximation for the binomial distribution. In other words, what we're going to do is we're going to take the normal curve, that curve that kind of fit on top of the binomial distribution, and we're going to use that curve in order to estimate or approximate the binomial distribution. So remember the normal curve? We basically had this kind of curvy graph, the bell curve, which was centered around mu, and we had these standard deviations on either side. And if you think about it, one of the things that we had seen from before was that this was basically estimating our binomial distribution. So in essence, what we had were like little graphs like this. I'm probably going to fail at making this perfect, but you get the idea. So we have this histogram like this. And so like this kind of keeps going on forever. And basically the idea is that we're going to use this main graph, this normal curve, to kind of estimate our binomial distribution. So the binomial distribution is actually dependent on two things, right? It's dependent on n and p, right? Our probability of something occurring and how many times we do something. So the only things we need to worry about now are our two variables. One of them is mu, but this we already know, right? Mu, we said, is the expected value. And mu is just equal to n times p. So that one is not too hard. But what about sigma? Sigma is a little more complicated, and it's not readily available. It's one of the things that makes standard deviation confusing for me, is that it's not a very easily understandable formula. And basically what it turns out to be is that if you take n to be sufficiently large, then your sigma is just going to be approximated by n times p times 1 minus p, and you take the square root of this. And this, if you recall, this is just called the standard deviation. Okay, so cool. So we have a way to get NRP and convert these into standard deviation, things for the normal curve. So does this make sense to ask? So remember when we're looking at the normal curve, right? It doesn't make sense to ask about a point at the probability at a certain point, right? Because since our widths are infinitesimally small, the probability is basically 0. It doesn't really make sense to ask about a certain point. So we have to look at some interval. But that's okay for us, right? Because our intervals are basically going to be, so if you think about it, like our intervals here are basically going to be these little bracket areas, right? So this is one interval. So that's what we're going to basically have. So if we think about this, the probability from A to B is the proportion of the area under the curve, or under the histogram, I guess. Histogram of the binomial distribution. Binomial distribution between, basically what we have is we want to approximate this a little, right? So what we want to do is there's going to be like some little factor here, some little factor here. So we'll add a 1/2 and a little 1/2 here, just to make things a little more easy to digest. And we'll do this between x is equal to a minus 1/2. A minus 1/2 and b plus 1/2. So we'll kind of budget a little to kind of see where this does things. So what this means is this is approximate to the proportion of area under normal curve. So here we can look at the area under the normal curve and look at this between the points x is equal to a minus 1/2 and b, so x1, x2 is equal to b plus 1/2. So here we're looking at the normal curve itself rather than binomial distribution. And this, if you remember, is when we're looking at the standard normal curve. This is just going to be equal to the proportion. So here we convert to standard normal of area under standard normal curve And here we have between, so here, remember that normally, we'll let these be z's. Normally we have to subtract off the mu and divide by standard deviation. So we have a minus 1/2 plus mu divided by sigma. Sorry, not plus, minus mu. And then z2 is b plus 1/2 minus mu over sigma. Now what this means is that the normal approximation to the binomial distribution can actually just be given by our phi. So in other words, if I take a plus a to b, this is approximately equal to phi of b plus 1/2 minus mu over sigma minus phi of a minus 1/2 minus mu over sigma. So let's kind of see how this helps us by an example. So let's suppose I randomly take a fair coin, and I toss it 100 times. So this should be a relatively easy example. So I take a coin and I toss it 100 times. So let me highlight this. And we want to know the probability of getting exactly 50 heads. So what's the chance of getting 50 heads? Well, in this case, we already know the binomial distribution, right? So the binomial distribution for this, P of 50, is given by 150, right? So we saw this earlier in our earlier videos, times 1/2 to the 50, times 1/2 to the 50, right? So here, remember, our binomial distribution is given by this formula. So this, if you try to calculate out, you get 100 factorial over 50 factorial times 50 factorial times 2 to the 100. And this turns out to be roughly 0.075795892. Now, you can sit here and calculate this, obviously, but like this is not something that you're going to want to do by hand, right? This is disgusting. It's really big, it's really massive, and you're going to have computational problems too, potentially. So instead, what we might want to do is find a numerical approximation. So what we'll do is we'll make a and b both equal to 50. We know our mu, right? Mu is equal to NP, so it's 100 times 1/2 is equal to 50. And we know our sigma, right? So sigma is equal to square root of p, 1 minus p times n. So this is square root of 50 times 1/2, which is square root of 25, which is 5. So what we have is we can approximate 50 to be phi of 50 plus 1/2 minus mu over sigma minus phi of 50 minus 1/2 minus mu over sigma. So let's plug in these numbers. Phi is, I guess, 50.5 minus 50 over 5 minus 50, 49.5 minus 50 over 5. So what do we get? We get phi over 1/10 minus phi over minus 1/10. So the 1/10, in case I went too fast, 50.5 minus 50 is equal to 0.5. So it's 1/2 divided by 5, which is just 1 over 2 times 5. Flip it and reverse it. So 1/10. So just as a little side note, in case that went fast. We have a little formula that kind of helps us deduce this. This ended up being 2 times phi of 110 minus 1. This, at this point, you look at the back of the book and you see that this is equal to 0.5398. And then this simple calculation gives you 0.0796. So you'll notice how this is actually really close to our solution. I guess, can I get both at the same time with my head not blocking the view? There we go. So yeah, so this is fairly nice and easy to see. And it was a much quicker example, right? Like trying to do the first one by hand is going to take too long. It's not going to work. Whereas this, you just look at the back of the book, you look at the approximation, you're done. It takes 2 seconds. So yeah, so these approximations are super nice when we're looking at binomial distributions. What we're going to look next is we're going to look at fluctuations in this, because as n grows, our curves are going to get smaller and smaller, or we're going to have certain things happen. So we're going to look at fluctuations in this in the next video. See you then.